Recently, we were introduced to the chain rule, which is a way to find the derivative of a composition of functions. Now, in section 3.5, we're introduced to an application of the chain rule, which is called implicit differentiation. And that's where we use the chain rule in order to find the derivative of a function that we don't know an explicit formula for yet. Okay. So we'll be focusing on finding dy dx or y prime. So anytime that we see the variable y in the equations here, more generally it could be any dependent variable, but for right now, if we see the variable y and we're asked to find y prime or dy dx, we will be taking the derivative of the variable y by use of the chain rule. So I'm going to start with an explanation of what is an explicit function versus an implicit function. Okay? And an explicit function would be if we can solve an equation for y as a function of x, that would be an explicit function. If we cannot solve for y as a function of x, which in many cases will be the case, or if it might be too expensive, maybe algebraically expensive for us to do so, but we still want to know the derivative, dy dx, okay, then we can just assume that y is a function of x, or a combination of functions of x, and we can still try to find the derivative by the application of the chain rule. Okay, implicit differentiation is the name that we give to this process, and we can start taking derivatives now of inverse functions. That is, if we have a function that is the inverse of another function we already know the derivative of, we can start finding what the derivatives would be of these inverse functions. And in this section, we'll look at the derivatives of the inverse trigonometric functions, such as arcsine, arccosine, arctangent, okay, arcsecant, arccosecant, and arccotangent as well. And in the next section, we'll introduce the derivatives of logarithms, which can also be derived because the logarithm functions are inverses of the exponential functions, which we've previously found the derivatives for. Okay, so for section 3.5, let's start with what is an explicit function versus an implicit function. I already tried to explain it a little bit here. An explicit function, okay, if we can express the dependent variable in terms of the independent variable by an explicit equation. Okay. If y, so if y can be, let's say, solved as a function, okay, or functions of x. Okay, so maybe another way to say that basically is, okay, if we can, let's say, I'll put in quotes here, easily find y is equal to f of x. Okay, so that would be by using algebra to find y is a function of x. Or functions, if we can find a y1 as f1 of x, so one function of x, y2 as an f2 of x, y3 as an f3 of x, etc., for as many functions as we may need to define, okay, when we are trying to solve for y. Okay. What do I mean by this? Well, I'll show you an example in just a second. Now, an implicit function, okay, an implicit function is if we assume that y is a function of x already, or a combination of functions, okay, or y can be expressed as a combination of functions of x. So we are working on the assumption that y is dependent on x. Right? Still, with the definition of a function being that if we choose a value for the independent variable, we would get one and exactly one value of the dependent variable. Okay, now herein lies why we can see through the geometry of certain equations why it would be we might end up requiring a combination of functions. Okay, so let's take, for example, Okay, consider the unit circle. It's easy for us to consider the geometry of the unit circle, or it's easy to sketch. We can look at its equation. The unit circle has the equation x squared plus y squared is equal to 1. Okay. Its graph is a graph of a circle. It has a radius equal to 1, and the center is 0, 0, the origin. Right, center at 0, 0, and the radius is equal to 1 unit. Right, so of course it has points on it like 1, 0, 0, 1, negative 1, 0, and 0, negative 1, and certainly many other points as well. Right, so this would be like root 2 over 2, root 2 over 2, for example. Okay, this equation right here, x squared plus y squared is equal to 1. First, we note we can solve this for y. Right? We can, if we wish, solve the equation for y. Okay? But if we do that, we're going to get more than one combination. Right? We're going to get y as, in this case, 2 functions of x. And that makes sense geometrically here as well. If we consider that if we were to choose a value of x, okay, let's say if we choose, for instance, x is equal to root 2 over 2. By that choice, we can see from the graph, okay, that this picture here, this circle does not pass the vertical line test. In other words, this circle itself is not a single function. If we choose x is equal to root 2 over 2, okay, that corresponds to a vertical line like this, x equals root 2 over 2, and that vertical line intersects the graph of the unit circle in 2 locations. So this is not a function by itself, right? X squared plus y squared is equal to 1 is not a function. Okay, we could see that symbolically then if we try to solve this equation for y. We get what, y squared is equal to 1 minus x squared, but now solving for y, we get y is equal to plus or minus the square root of 1 minus x squared. Now this means that either y is equal to the positive square root of 1 minus x squared, or that y is equal to the negative square root of 1 minus x squared. How do we interpret these geometrically? All right, go back to our picture. This first one here, where y is equal to the positive square root of 1 minus x squared, first consider that the output of a square root is never negative when we're dealing with real numbers. So the right-hand side of this equation is not negative, and it's equal to the left-hand side of the equation. So therefore, it must be for this equation, since the right-hand side is never negative, the left-hand side is also never negative. All right, so the y value over here is strictly positive. So this is where the y value is strict or non-negative, greater or equal to 0. Okay, so that would correspond then to the upper half of this graph, because on the upper half of this graph, the y values are never negative. All right, so if we just take the upper half of the graph of the unit circle, okay, let's say this right here, that would be expressed by this. Okay, and this is a function, right? This does pass the vertical line test. It is vertical line test approved, right? Now, on this curve right here, if we were to choose x is equal to root 2 over 2, it could only correspond with a quadrant 1 point on this curve. So this is one function of x we could get from the x squared plus y squared equals 1 equation. So I'll call this one y1. This is y1, which in function notation would be like an f1 of x, right? It is one function that we can get for x, and this is an explicit now function of x. The other function, we have the right-hand side. Remember, again, the output of a square root with real numbers is never negative. So if the square root itself, this piece right here, is never negative, then putting a negative sign in front of it guarantees that this expression is never positive. right? This is never positive. And that means if it's equal to this y over here, it means that the y value over here is also never going to be positive. All right, so for this second equation, we have that y is less than or equal to 0. So here I have, let's see, I'll call this one I'll call y1, or this one I'll call y2. Okay? It is a second explicit function of x. Call this f2 of x. Okay? So we have an f1 of x, we have an f2 of x. The graph of this one down here would be then the lower half of the unit circle, of course, because that's where the y values are never going to be positive. Here we go. All right, so we have a lower half of the unit circle. We get a little better on the symmetry there. There we go. Okay, so here's our y1, which is our f1 of x curve. This is our y2, which is f2 of x curve. It is vertical line test approved. This is certainly a function, so we can call it a function. What we couldn't do is we couldn't go up here. We couldn't call this f of x. Why can we not call this f of x? Because for any value of x that is in the domain, that's between -1 and +1, for any value of x that we plug in here from the domain, if it's strictly between -1 and +1, notice by the plus and minus, we're going to get more than one output. So we can't call this f of x right here. All right? It does not satisfy the definition of a function, that there is only one output for any input that you choose in the domain. All right, so if we put x equals 0 into here, we get two values of y. It is not a function. So if we want to use functions and all the things that we do with functions, okay, then we need to split this up into a combination of functions, which we can interpret geometrically as breaking up the graph until we have pieces of the graph that each independently would pass the vertical line test, and then defining each of those pieces by an explicit equation. So we have two explicit functions of x here. Okay, when we were looking at the equation x squared plus y squared is equal to 1, by the way, this equation right here, okay, that would be an implicit equation. Okay, this is the implicit form, where we are assuming that y is a function of x. We can see from the equation, this equation written like the way it is, if we plug in a number x that is within the domain here, we know we're going to get some value or values of y. So y certainly is dependent on x. So this is the implicit form, where we know that y depends on x. We just don't have it written out explicitly how y actually depends on x, because we have not yet at this stage done the algebra. And in many cases, we're not going to want to do the algebra. Okay? And that's part of this section that we're talking about right here. In this case, it's not that bad to do the algebra. Okay? But when we rewrite these equations, okay, as these combinations here, we have written y in as explicit functions of x. Okay, so these are the explicit forms. The explicit forms for y as a function of x. Now, the calculus we've done so far, we should be able to apply to both of these forms. That is, geometrically, we can see that, for instance, you know, if we wanted to find the slope of the tangent line, let's say at this point right here, we could either, if we knew how, determine what this derivative is at this point implicitly by using this equation here, if we can avoid the upcoming algebra, or if we solve for y as a function of x at that point, that is, if we were to explicitly solve y as a function of x and get this, which puts us on that upper half of the curve, which contains that point specifically, then we could use our explicit function right here and take the derivative, interpret it as the slope of the tangent line, and proceed as we normally would. So let's do what we already know how to do, which is when we have an explicit function of x, let's find the derivative. Okay. Now we have two different functions of x to do this for. Okay, so let's do this. Let's find the derivative of y1 with respect to x. Okay, and then let's find the derivative of y2 with respect to x. Okay, and so this would be doing so explicitly by using the explicit functions of x. Okay, so first, dy1 dx, okay, is the same as saying that we're taking the derivative with respect to x of f1 of x, which is the square root of 1 minus x squared. Okay, the square root of 1 minus x squared, right? The positive principal square root. Okay, now we can rewrite this as a composition with a composition where you have a polynomial inside of a power function. Then we can apply the chain rule to take this derivative. So this is 1/2 times 1 minus x squared to the negative 1/2, and then we apply the chain rule, so we multiply this by the derivative of 1 minus x squared, which gives us negative 2x. Okay, and then finally we can simplify that and clean it up a little bit. The negative 1/2 pushes this to the denominator. We have a 2 canceling a 2. Okay, so we're going to have negative x over the square root of 1 minus x squared. Okay, and again, that is the derivative of y1. So that is what, this is the expression we would use to find the slope of the tangent line if we're on the upper half of the unit circle. But only if we're on the upper half of the unit circle would we use this particular equation. Now what about the derivative for y2, or of the function f2 of x? Okay, notice the only difference here is that we have a negative then in front of, in front of the radical. dy2 dx, the derivative with respect to x of the negative square root of 1 minus x squared. Okay, so we can factor out the negative, and then it's the same as the derivative we just found otherwise, right? We take the negative out as a constant, so we have the derivative of the square root of 1 minus x squared. Well, then the answer to that is going to be negative, okay, this answer right here. So the opposite of the answer that we got above. Okay, and that simplifies as x over the square root of 1 minus x squared. Okay, and here's our expression for the derivative with respect to x of y2. So this is the explicit expression we would use for the derivative if we were on the lower half of the unit circle then. Okay. Why the difference in these expressions? How can we interpret that geometrically? How come this one, okay, on the upper half, how come we have a negative sign, but on the lower half we have a positive sign? Okay, let's let x equal something like the square root of 2 over 2, right, and find the tangent lines. Okay, so let's find tangent lines, the tangent line equations, okay, on the unit circle. Okay, so let's say we have y1 prime evaluated at root 2 over 2. Okay. So this is our y1 prime. Plugging into that, we get negative root 2 over 2 over the square root of 1 minus root 2 over 2 squared. Root 2 over 2 squared is 1/2, so this is 1 minus 1/2, which is equal to 1/2, so we have the square root of 1/2. Okay, so negative root 2 over 2 over the square root of 1/2, but the square root of 1/2 is root 2 over 2. So this simplifies to equal negative 1. Does that make sense geometrically? When we use the explicit form of the derivative on the upper half of the unit circle and evaluate it at x equals root 2 over 2, okay, we got that the slope of the tangent line would be negative 1. Right? That seems to make sense because in quadrant 1, okay, in quadrant 1 on the unit circle, right, the tangent line clearly has a negative slope. Right? It is decreasing. So this seems to make sense then that if the denominator here, which is a square root, a principal square root, if the denominator is never negative, right, never negative, then the fraction is determined to be either positive or negative by virtue of the numerator. Well, if the x value in the numerator is positive, then we're going to take the opposite of that and end up with a negative slope. And that does correspond with what happens in quadrant 1. In quadrant 1, the x value, okay, in quadrant 1, the x value is going to be positive. Okay? And if the x value is positive, then the associated slope of the tangent line is negative. In quadrant 2, where we would also be on the upper half, there the x value would be negative. And if the x value is negative, then this is going to flip that to a positive, which is going to give us a positive slope, which would be true. We would have an increasing function in quadrant 2. So we can already see how the geometry is going to work out here if we go, if we're on the lower half of the unit circle, if we're using y2 instead. So let's see what happens at x equals root 2 over 2. That's if x is a positive number. We can see that on the graph of y2, the tangent line there would have a positive slope. So it makes sense that the formula would not have the negative sign in front of it, because if x is positive, then this fraction is positive, because the denominator again is going to be non-negative. Okay. Well, the denominator is going to be positive, and the denominator can't be 0 anyway, right? Or it would be undefined. Okay, so y2 prime then. y2 prime of root 2 over 2, it's almost the same expression, right? It's just it doesn't have a negative in front of it. So we have root 2 over 2, okay, over the square root of 1/2, and that just equals positive 1. Okay, so that does correspond, okay, to the geometry. It does make sense with respect to the geometry of the unit circle. Okay, solving for y as a function of x explicitly, or solving for y as a combination of functions of x explicitly, can potentially be algebraically expensive. And in fact, it can also be proven to be, in many cases, impossible to do. So we want to be able to apply calculus when we know that geometrically that the slope of the tangent line should exist, and we should be able to find the derivative and calculate its value as well. We would like to avoid the algebra that would be required in doing this explicitly. We want to be able to find the derivative instead implicitly. Use this form right here to find out what y prime would have equaled. And here's where we can apply the chain rule to do so. We introduce the idea of implicit differentiation. Okay, so what we do is in an equation we assume that y is a function of x, or that yi is equal to fix, okay, for many I. So in other words, we have many functions of x that we could get. In other words, right, y is dependent on x is what we're saying. And we might have more than one y value for a given x value, in which case we would need multiple functions. Okay? And we're going to assume that. Okay. Okay, then let's say we have a function written f of xy. So I'll use a big F here. Big F of xy. Then that function can instead be expressed f of x, comma, let's say f of x, or fi of x. Okay, depending on where, on which of those functions we happen to be looking at. Okay, and then this means that we can express f entirely as a function of x if we knew explicitly how y was a function of x itself. Okay, and when finding big F prime, then we're going to use the chain rule to multiply by y prime or dy dx for any term where we differentiate y. Let's take a look at an example so you can see what it is that I mean. So for example, find y prime, a formula for y prime for the unit circle, and do so implicitly. So we start with the equation of the unit circle, x squared plus y squared is equal to 1. Okay. And now we take the derivative, and we take the derivative of both sides. Just as we do in algebra, if you apply an operator to one side, you can apply it to the other side, and you still have balance of the equation. So if we take the derivative of the left-hand side of the equation, it would be equal to the derivative of the right-hand side of the equation. Okay. So we have the derivative with respect to x of x squared plus y squared. And on the right-hand side, we have the derivative with respect to x of 1. Right, we've applied the differential operator to both sides. Okay? And now note, we are assuming that y is a function of x, or that y is some combination of functions of x. Okay? So that is to say that when you see y squared, you can think of it as some function of x that we don't know what that function of x is yet, some function of x that is being squared. And then how would it look to take the derivative of such a thing? Well, we're taking the derivative with respect to x, okay, with respect to x. If we take the derivative with respect to x of some function of x contained or composed within the squaring function, then we would apply the chain rule. All right, this is exactly where we would need the chain rule. All right, because now whenever we look at something like y squared, as long as the derivative is with respect to x, and we're taking and we have an expression like y squared, we think of that as a composition of functions. Y is already a function of x that we just don't know what function of x it happens to be, nor do we need to know what it is right now. And that function of x is then being squared. So we have a composition. So by the chain rule, this derivative would be done by first taking the derivative of the outer function, which is move the 2 to the front, leave the inner function alone, that f of x, raised to the power of 1, that's the general power rule, and then multiply by the derivative of the inner function. And so that would be times f prime of x. Okay. Now, if y is equal to f of x, then y prime is equal to f prime of x. So this is the same as saying that we have 2 times y prime. So that is the derivative of y squared with respect to the variable x. When we are assuming that y is a function of x, the derivative of y squared with respect to x would be 2y y prime. It is an application of the chain rule. So we started by taking the derivative of the outer function by the general power rule in this case. So we get 2 times y to the first. And then we multiply by the derivative of the inner function. And the inner function was y, which is a function of x. And so the derivative of y with respect to x is y prime. Or in Leibniz notation, this would be 2 times y dy dx. Okay? And that's the other way that we could write it. So anytime we run into a y, when we're differentiating that y with respect to x as the input variable, we need to tag on a y prime by virtue of the chain rule. And that's what is called implicit differentiation. Okay? So let's apply the differential operator now. Now the derivative with respect to x of x squared is still 2x. All right? We're taking the derivative with respect to x of x squared, it's just 2x. But when we take the derivative with respect to x of y squared, that's where we apply the implicit differentiation. Okay? So here's where we need it. Okay. Because y is an implicit function of x. Okay. And on the right-hand side, we have the derivative with respect to x of a constant, and that's just equal to 0. The derivative of a constant is equal to 0. Okay. All right, let's complete this. So we have 2x plus, by the chain rule, implicit differentiation, this is 2y times y prime. And then that equals 0. Now we have an equation that we can solve algebraically for y prime. Okay, let's solve for y prime. Or dy dx. You could also use dy dx in place of y prime. So how do you solve this for y prime? Treat y prime as a variable now. So I have 2y y prime is equal to negative 2x, and then divide by 2y, we get y prime is equal to negative 2x over 2y. And there's our y prime. There's our formula for the derivative, for the slope of the tangent line. And now this formula for the slope of the tangent line will work at any point on the curve such that we have the coordinates x and y for that point. And that's what allows this to work now in any quadrant, okay, in any quadrant we choose. Right? So Go back to the picture of the unit circle. Okay. If we were in quadrant 1, we're at the point root 2 over 2, root 2 over 2, where we have both an x and a y coordinate. If we were in quadrant 4, the point root 2 over 2, negative root 2 over 2 would be the x and the y, for instance. So I called y f of x earlier, right? Little f of x. So y prime would be f prime, right? But notice now that f prime is a multivariable function. The way we have it written here, we would have to know both x and y. How come we have to know y in this case? How come we can't get this solved just in terms of x? Well, we could. And if we did solve this to be just in terms of x, that's where we would be finding it explicitly. So if we tried to replace this y by what y equals in terms of x, that would require us going back and solving this equation explicitly for y, which gives us a combination of functions. And so it puts us back in the situation where we have to do all that algebra again to get the explicit functions. And sometimes that algebra is not even possible to do. It can be proven not to be possible to do if, for instance, solving a high-degree polynomial equation. This is less work to do it this way. And so what we can say is that, well, if x is equal to root 2 over 2, then from the equation of the unit circle, right, which is x squared plus y squared is equal to 1, from that equation, we can solve for y, and we get y is either plus or minus root 2 over 2. So we get the numerical values for y instead, okay, or we otherwise get them from the graph. We see them from the graph here, okay? And then if we wanted to find, let's say, the equation of this tangent line right here, I'll make this tangent line here a light blue, okay? I'll call this one L1. Let's find that. And then the equation of this tangent line here, okay, I'll call this one L2. And let's find those equations. Okay. Find the equation for the tangent line L1. Okay. So L1 is the tangent line to the unit circle, so to x squared plus y squared equals 1, and it goes through the point root 2 over 2, root 2 over 2. Okay. So the slope of that line, I'll call it M1, right, can be found by taking y prime, or formula for y prime, and plugging in the coordinates root 2 over 2, root 2 over 2. It's plugging in both an x value and a y value. Okay. And of course, this simplifies, right? I can cancel these twos with each other. So we just get negative x over y. Okay. And so by that formula, we get negative the x value divided by the y value. And that equals negative 1. And that matches with the answer that we got earlier when we did this explicitly. And then what would be the equation of the tangent line? Well, we have a slope of negative 1, and we're going through this point. Coordinates root 2 over 2, root 2 over 2. Okay, so the equation of the tangent line would be y minus root 2 over 2 is equal to negative 1 times x minus root 2 over 2. Okay, and that would be an equation of the tangent line. All right, let's see. In slope-intercept form, if we wanted that, it would be what y equals negative x, and then this would be plus root 2 over 2 plus another root 2 over 2. So that's plus 2 root 2 over 2, or just plus the square root of 2. And how about an equation for tangent line L2, which goes through the coordinates root 2 over 2, negative root 2 over 2. We can find the slope of that tangent line by going to our y prime formula here, negative x over y, and plugging in the x and y coordinates for that point. Okay. So let's find the equation for the tangent line L2. So M2, say that's the slope of L2, is found by the formula for y prime, right? With the coordinates root 2 over 2, negative root 2 over 2. And so that's, the formula was negative x, so negative root 2 over 2 divided by y. And the y coordinate now is negative root 2 over 2. And this just simplifies to 1. So the slope of that line is 1. And the coordinates of the point, root 2 over 2, negative root 2 over 2, that gives us then the equation for the tangent line. So y plus root 2 over 2 is equal to 1 times x minus root 2 over 2. And there's an equation of the tangent line. Okay, or in slope intercept form, y equals x minus root 2 over 2 minus another root 2 over 2. So that's minus 2 root 2 over 2, or just minus the square root of 2. So y equals x minus the square root of 2. Okay, so we found the equations of the tangent lines here by using the implicit form of the derivative. We found y prime through implicit differentiation, which is an application of the chain rule. Anytime that we're going to take the derivative implicitly, let's apply the differential operator to both sides of the equation. Really, that's what we were doing all along anyway. I mean, even if we go back to the explicit form, okay, we're not only taking the derivative of the right-hand side. Let's say we're taking the derivative of this equation right here. We don't only take the derivative of this expression, we're actually taking the derivative of y1 and saying it is equal to the derivative of this expression. That's exactly what we did here, right? That's why we write dy1 dx on the left-hand side, and we take the derivative of the right-hand side, right? So we're saying the derivative of the left is equal to the derivative of the right. So that really hasn't changed. We already were taking the derivative of both sides of the equation. Now we need to be more clear about that in our notation. The derivative of the left equals the derivative of the right. Using the Leibniz notation helps to clarify the variable that we're interested in taking the derivative with respect to. Okay? Now let's note, when we write something like, if we take the derivative with respect to x of x, that is dx over dx, that is equal to 1. But if we take the derivative with respect to y, that's equal to dy dx, or y prime, right? That's different, right? So when we take the derivative with respect to x of y squared, we don't just get 2y, right? We get 2y times y prime by the implicit differentiation, because the variable of differentiation is the variable, the independent variable in the implicit function for y. Compare that to when we take the derivative of x squared, right? So the derivative with respect to x of x squared is just 2x. But the derivative with respect to x of y squared is 2y. Then we tag on by the chain rule times y prime. That's the implicit differentiation right there. It's the chain rule in action when we don't have y solved as an explicit function of x, but we're trying to take its derivative with respect to x. Okay, so a note there. Right, the Leibniz notation makes it clear which is the variable of interest that we're taking the derivative with respect to. And then in many cases, then when we do the implicit differentiation, in most cases, we will end up with a derivative formula, okay, that is going to have both x and y in it. So our derivative formula is actually then a multivariable function itself. That is, we would need to know more than one input variable. We need to know both x and y in order to find y prime. Notice we now have three variables here. X, y, and y prime are the three variables in this equation. Let's say we wanted to find now y double prime. Find y double prime, the second derivative. That is second derivative of y with respect to x both times. So we apply the differential operator twice, both times with respect to x. Okay, for the unit circle, the second derivative. Well, we already have the unit circle equation is x squared plus y squared is equal to 1. Right, that's our unit circle. And we have now a y prime, or dy dx. dy dx, which is equal to y prime, we just found is equal to negative x over y. Okay, so we've already concluded that. Okay, and now we can find the second derivative, y with respect to x both times. Remember, notationally, that's the same as saying we're taking the derivative with respect to x of dy dx. That's why we have the d squared in the numerator and a dx squared in the denominator. Okay, or y double prime. Okay, so this is the first derivative with respect to x of y prime. And y prime is now a function of both x and y is a function of x, right? An implicit function of x. So in the differentiation of y prime with respect to x in the second time, okay, we're going to have to treat y as an implicit function of x. Otherwise, we're going to apply the normal quotient rule to this. Apply the quotient rule to this with respect to x. It's just when we get to y, if we take its derivative, the derivative of y will be y prime. Okay, and the derivative of y prime is y double prime. Okay, so we're applying the differential operator then to both sides of this equation. Derivative with respect to x of y prime is equal to the derivative with respect to x of negative x over y. And to differentiate the right-hand side, we're going to need to start with a quotient rule. Okay. On the left-hand side, the derivative of y prime with respect to x is just y double prime. Okay. On the right-hand side, so we get, okay, the quotient rule starts with low d high, so we start with the low function, which is y, and then we multiply by the derivative of the higher function, so the derivative of negative x. I'll just write it out there with the Leibniz notation. Low d high minus, now the high function, so negative x, times d low, and so here's where we take the derivative of the denominator, okay, over the denominator squared. So we get y times derivative of negative x with respect to x is negative 1. And then we get plus x, and the derivative of y with respect to x is dy dx, or y prime. And the denominator here is y squared. Okay, so we can clean this up a little bit. We have y double prime is equal to negative y plus xy prime over y squared. And that is indeed a formula for y double prime. But this requires, okay, this now requires, let's call this f double prime then. It requires that we know x, y, and y prime, right? All three of those quantities would need to be plugged in now in order to find y double prime. So let's go a little further though. Let's find y double prime, okay, in terms of just x and y only, okay, alone. We can do that because we already have an explicit formula for y prime. This is an explicit formula for y prime. Y prime equals negative x over y. So we can plug that in. Y double prime is equal to negative y plus x times negative x over y, because y prime is equal to negative x over y, and that's over y squared. Okay, so we can clean this up here. I'm going to multiply the top and the bottom of this by y. Okay, that's going to cancel this out. So we have y double prime is equal to negative y squared, okay, and then minus x squared over y cubed. So there's a formula for y double prime in terms of just x and y as the inputs then. So if we know the coordinates of the point on the curve, we can find the second derivative, okay, at that point. Okay, so let's see. Let's find y double prime at the point root 2 over 2, root 2 over 2, for instance. So y double prime at root 2 over 2, root 2 over 2 would be negative root 2 over 2 squared minus root 2 over 2 squared over root 2 over 2 cubed. And this quantity will tell us geometrically about the curvature of the function. We'll talk more about that later in the course. But here we're just seeing that this is something we can do. We can use a higher derivative and we can evaluate it at a point as well. So this is negative 1/2, right? The square of root 2 over 2 is 1/2. Minus another 1/2, and then the denominator we would have, well, this is going to be right, well, we got 2 root 2 over 8, right? So negative 1/2 minus 1/2 on top gives us a negative 1. The denominator is root 2 over 4. Okay, so this is negative 4 over root 2, or if I rationalize the denominator, negative 4 root 2 over 2, which is equal to negative 2 root 2. This tells us really about the curvature. Okay, I'll give you a hint to that right now, but we'll get back to it later. It's telling us that what's called the concavity of this curve at this point right here. When the concavity is negative, as it was here, we found it to be negative, it means that the curve is concave down, and so it's an inverted bowl-shaped curve here. That is, that you can imagine it if it were raining on this, the rainwater would wash right off the side. Okay. If we were to evaluate the concavity down here at this point, we would find it's concave up here. Notice that this is a bowl that is opening upwards. If it were raining onto a region that were shaped like this would collect rainwater instead of it rolling off the side. So we are concave down at this point, is how we interpret that. Okay, it is the rate of change of the rate of change, or the rate of change of the slopes of the tangent lines. And that's what we found geometrically. Okay, here we're just doing it formulaically and symbolically, saying, well, we can find a second derivative. If we have an explicit formula for y prime, we can then find y double prime, so on and so forth. Okay, let's take a look at another example now about something that involves, we just did something with a quotient rule where we had implicit differentiation. Let's take one that also has a product rule. Find y prime for curve x to the fourth plus x squared y squared plus y cubed is equal to 3. So I'll call this part A. Find y prime. Okay, and then for part B, okay, find the equation of the tangent line at the point 1, 1. Verify this is on the curve. Okay. Call this f of 1, 1 is equal to 3. So I'm saying that this, the thing on the left-hand side right here, is a multivariable function. All right, we have an f of xy is equal to x to the fourth plus x squared y squared plus y cubed. Introduction to multivariable functions in your calculus class. Okay, all right, if we plugged in 1 is x and 1 is y, we would get 1 to the fourth plus 1 squared times 1 squared plus 1 cubed. That's 1 plus 1 plus 1, which is equal to 3. So we can verify that this is in fact a point on this curve. Okay, if we were to graph this. Now, we want to find the equation of the tangent line, we want to find y prime. Notice we would not want to solve this explicitly for y. If you would like to try to solve it explicitly for y, okay, it's a cubic equation, you would have to find multiple functions for y. It is a nightmare of algebra to have to solve for y. So let's just say right here, note, we do not want to go down that road. We do not want to find y explicitly as a function of x. Okay, we want to find y prime by using implicit differentiation here, though. So we do that by taking the equation that we're differentiating, and we apply the differential operator, that's with respect to x, to both sides of the equation. Okay, so for part A, the derivative with respect to x of x to the fourth plus x squared y squared plus y cubed is equal to the derivative with respect to x of 3. So I've applied the differential operator to both sides of the given equation. Now the right-hand side is real easy. The derivative of 3 with respect to x is just 0, because 3 is a constant. The derivative of the left, okay, we're going to apply the differential operator to each term, starting with x to the fourth. And since it's with respect to x, we just apply the general power rule as normal, 4x cubed, and we're done. Now I'm going to jump to the last term, y cubed. Okay, the derivative of y cubed is going to require implicit differentiation. First, we're taking the derivative of a y function, but with respect to x. Okay, so y is considered to be a function of x. And that y is contained within the cube function. So we start by taking the derivative of the cube function, the outer function. That's going to give us 3 times y squared. We've left y alone for the moment by the chain rule. Then we multiply that by the derivative of y with respect to x, which I'm going to call y prime. That's our implicit differentiation right there. Implicit differentiation was done right there. Okay. and that is a y prime, or a dy dx. Now how about this middle term right here? Well, this middle term is a product, so we're going to need the product rule. Right. So for this, right, we're going to start by using the product rule, and in the product rule, when we do take the derivative of the y squared piece, that's when we're going to have to apply implicit differentiation to the y squared. So I'm going to start by taking the derivative of x squared. The derivative of x squared is 2x. And when we take the derivative of the x squared, we can leave the y squared alone. That's part of the product rule. Right? Then we add. Now I'm going to leave x squared alone. Leave x squared alone, and now take the derivative of y squared with respect to x. The derivative of y squared with respect to x is 2y times y prime. Okay? And I'll put a plus sign here between the terms. So there is our implicit differentiation right there. Okay? It was within the product rule. So this is the product rule right here for that middle term, and we had implicit differentiation done when we took the derivative of the y factor of this term. Now we're not done. We've taken the derivative here, but now we need to find out what y prime is itself. So we need to solve this equation now, okay? Solve it for y prime. So we can do that by collecting the terms that have a y prime in it. We have this term and this term. We have two terms that have y prime. This term and this term have y prime in it. So I'll keep those. I'll write this one as 2x squared y prime. And then this one as plus 3y squared y prime. And then move the other terms to the other side of the equation. So negative 4x cubed minus 2xy squared. Okay, so I've isolated the terms of y prime. Now factor out the y prime. So y prime times 2x squared y plus 3y squared. And the right-hand side is negative 4x cubed minus 2xy squared. And finally, divide to isolate y prime. So y prime is equal to negative 4x cubed minus 2xy squared over the quantity 2x squared y plus 3y squared. And there's our formula for y prime, where we have now expressed y prime as a function, okay, f prime. Let's say if y is equal to f of x, then this is f prime, but it's f prime of x and y, right, is a multivariable function. If we know both x and y at a particular point on the original curve, we can plug that x and y into this formula to find the slope of the tangent line at that point. Right, and we found y prime without having to solve for y originally. We don't want to know what y is as a function of x, not for a case like this. But for part B, find the equation of the tangent line at 1, 1. So 1, 1 is an x value, y value. Okay, so find the tangent line at the point where x and y are both equal to 1. So we find the slope of the tangent line by plugging 1 and 1 in as the x and y values into the y prime formula. That gives us negative 4 times 1 cubed minus 2 times 1 squared over 2 times 1 squared times 1 plus 3 times 1 squared. Okay, and what does that equal? So we have negative 4 minus 2 on top is negative 6, and the denominator we have 2 plus 3, which is equal to 5. So there's our slope. Our point is the point 1, 1. Our slope is negative 6/5. So the line is y minus 1 is equal to negative 6/5 times x minus 1. There's the equation for our tangent line. Or if we want a slope-intercept form, y equals negative 6/5, right, x. Okay, and that's what, plus 6/5 plus 1 is plus 11/5. There's the equation of the tangent line. Now, the book does a pretty good job showing some examples of some functions graphed whereby we would not want to solve explicitly for y as a combination of functions of x. One of the examples that I like is the folium of Descartes. It's x cubed plus y cubed is equal to 6xy. This is the look of the graph of the folium. Okay, and we can see that it does not pass the vertical line test if we are right within this region right here, right? If we choose a vertical line somewhere like here, we would get three different values of y for that chosen value of x. So for this region, we would need 3 functions described. And here you get the graphed 3 representative functions, for example, right? Each one of these is a function in its own right, and they're each pieces that, when put together, would give us the complete folium. Okay. Now, solving for those functions explicitly is an awful lot of algebraic work, and in some cases it's not even possible to do. Right, it gives you the formula, well, it uses the formula for solving a cubic, which is nasty in its own right. If you wanted to solve a y cubed equation for y, you can solve it by the cubic equation, the roots of the cubic equation formula. But once we get to equations like this, it's no longer even possible to solve for y explicitly. So certainly we want to be prepared to be able to find y prime, a derivative of y with respect to x, without having to do the algebra at the start. And not just for functions that are polynomial. What about functions that are also combinations with trigonometric functions in polynomial, or exponentials and trigonometric, for example, and polynomial? Let's try an example like that right now. Okay. Find the tangent line equation, okay, to e to the y times the cosine of x is equal to x plus 1 at the point 0, 0. So this function here is a combination of exponential, right, trigonometric, and polynomial. All 3 of those thrown together here. Let's verify that this is a point that satisfies the equation. E to the 0 times the cosine of 0 is equal to 0 plus 1. Is that true? Well, e to the 0 is 1, cosine of 0 is equal to 1, and 1 times 1 is equal to 0 plus 1, which is 1. So yes, this is a point that lies on this curve. We don't want to solve for y. We could solve for y explicitly here. It's not that hard. We could divide by cosine of x and take the natural log of both sides. We could get that. Then we'd have to take the derivative of y with respect to x using the derivative of a natural log, which we haven't quite looked at yet. But we do already have the technique that allows us to do that, and that technique is implicit differentiation. So let's find y prime implicitly. Find y prime implicitly right now. Okay. So we'll take the derivative with respect to x of the left-hand side, and that is equal to the derivative with respect to x of the right-hand side. On the left-hand side, we're going to need a product rule. So in this case, I'm going to take, so for the product rule, first I'm going to take the derivative of e to the y. Okay, so the derivative of, okay, I'll write it out here. The derivative of e to the y, and then that's times the cosine of x, plus, now we'll leave e to the y alone, and multiply that by the derivative of cosine of x. On the right-hand side, the derivative of x plus 1 is just equal to 1. Okay, now the derivative of e to the y, when it's with respect to x, we need implicit differentiation. First, the derivative of e to the y is e to the y. And now because y is an implicit function of x, we multiply that by y prime. There's our implicit differentiation then right there. Okay, then that gets multiplied by the cosine of x, plus now we have e to the y times negative sine of x, because the derivative of cosine x is negative sine x, okay, and then that equals 1. So now we can use this equation to solve for y prime by substituting the values of x and y at the fixed point. We don't have to solve this equation for y prime first before plugging in x and y. Okay, so y prime is a third variable within this equation. So let's plug in y is equal to 0, for instance. So we get e to the 0, and then we have times y prime. And then x is equal to 0, so we have cosine of 0, plus e to the 0 times negative sine of 0 equals to 1. Okay, so e to 0 is 1, cosine of 0 is 1, so we have y prime plus 1 times sine of 0 is 0, so that's just plus 0, and that equals 1. So we have y prime, okay, well, y prime at the fixed point 0, 0 is equal to 1, and so there's our slope of the tangent line. Okay, so the equation of the tangent line is, well, y minus 0 is equal to 1 times x minus 0. In other words, y is equal to x is the equation of the tangent line. Alright, so now let's take a look at the inverse trig functions and some of their derivatives. If you take a look at the worksheet I provided for you, I ask you to find y prime or dy dx and give you some of the answers here as well. Okay. All right, here's some of the formulas for the derivatives of the inverse trig functions. We can prove these formulas, derive them by using invertibility and implicit differentiation. Let's start with the derivative of the arcsine function. If we recall, the arcsine function, the inverse trig functions, defining arcsine, that is like the arcsine of x is equal to y. Okay, that is built as the inverse of the equation the sine of y is equal to x, and we can interpret the sine of y is equal to x in the rectangular coordinate system, and also in the right triangular trigonometry. Now let's take a look at the right triangular trigonometry for the sine of y is equal to x. A right triangle with an angle in it with the name y. The sine of that y is equal to x, or the ratio x over 1 means the opposite side is x and the hypotenuse is 1. And then we can solve for the adjacent side through the Pythagorean theorem, right, and get that the adjacent side then is the square root of 1 minus x squared. Right? The adjacent squared plus x squared is equal to 1 squared. Solve for adjacent. You get that the adjacent side is equal to the square root of 1 minus x squared. Okay, let's take a look at the graph of the function, really, f of x is equal to the sine of x. All right, so that graph is the sine wave function. We'll get a little taller than that. There you go. All right, you get the idea. F of x equals the sine of x, right? So there's the y-axis, here's the x-axis. And this is a function. It passes the vertical line test, but it is not invertible, right? It fails the horizontal line test. But if we want to be able to invert this function, which we certainly would if we wanted to solve equations like, let's say, the sine of x is equal to 1/3. What's the value of x that makes this true? Well, one solution to this equation would be that x is equal to the arc sine of 1/3. Now, in fact, there's more than one solution. Right? If this is 1 right here, then 1/3 would be maybe, let's say around here. Right? That means we would have solutions to this equation, sine of x is equal to 1/3 here, 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 right? We have an infinite amount of solutions to this equation. But if we wanted to start by just finding one of those solutions, we should build an inverse function. Okay, and in order to build an inverse, we should restrict the domain. Okay. Restrict the domain of f of x equals sine x, okay, in order to build the arc sine function. All right, sine to the negative 1, the inverse sine or the arc sine function. So we choose as the restriction for the sine function, the principal restriction, to be this window right here. Okay, and that's from negative pi over 2 to positive pi over 2, which in terms of the unit circle, right, the input to the sine function between negative pi over 2 and positive pi over 2, in terms of the unit circle, means that we are within between quadrant 1 and quadrant 4 when we are dealing with the principal branch of the sine function that is invertible. Okay, so we choose as a restriction negative pi over 2 is less than or equal to the input variable, in this case x, is less than or equal to pi over 2. Okay, and so that gives us a sine function restricted, looks something like this. Okay, so it goes up to 1, down to negative 1. All right, this is negative pi over 2. This is positive pi over 2. This is the function y is equal to the sine of x on the restricted domain. And this is invertible. This now passes the horizontal line test. And we invert it by switching the x's and the y's with each other. Okay, so we switch x's and y's, so that is we take the domain negative 1 to positive 1, and the range from negative pi over 2 to positive pi over 2. Okay, and the function would look like this. Okay, when we switch all the x's and the y's, and this, okay, would then be the arc sine of x function. Okay, so its domain is from negative 1 to positive 1 inclusive, and the range is from negative pi over 2 to pi over 2 inclusive. So now, when we solve an equation like x equals the arc sine of 1/3, we'll be finding a value of x that is between negative pi over 2 and pi over 2, such that the sine of that x is 1/3. Okay, so the solution of this equation, arc sine of 1/3, okay, that's going to be this. Okay, this solution right here. Of all the infinitely many solutions that we can get to the equation sine x equals 1/3, the one we're solving for here is specifically that solution right there. Then we can use the symmetry of the sine function, that is periodic symmetry, reflective and rotational symmetries, like within the unit circle, for example. Okay, and again, the periodicity of the sine function in order to find all the other solutions. Okay, that's how the arc sine function is designed. All right, that's what it's meant to do. Within right triangular trigonometry, okay, when we say we're solving the y is equal to the arc sine of x, we're thinking of that's the inverse of this situation, where the sine of y is equal to x is an equation where y, the input, was an acute angle within our right triangle here. Then the arc sine of x would tell us y. That means we are going to be told the angle or the input. Okay? So y is the input to the sine function. Okay, which can be either an angle or an arc length, depending on the interpretation we have. Okay, depending on the units that we're using as well. Okay, and whatever the application is. We're going to use invertibility and the fact that we already know the derivative of the sine function, okay, in order to find the derivative with respect to x of the arc sine of x. Okay, here's what we do. Let y equal the arc sine of x, then by invertibility the sine of y is equal to x. Okay? And we're trying to find the derivative of the arc sine of x, and if y is equal to the arc sine of x, then what we're being asked to find is dy dx, or y prime. Because y prime, all right, because dy dx would be derivative with respect to x of arc sine, since we've let arc sine of x equal to y. So we're trying to find dy dx using this equation, and that's where we're going to need the implicit differentiation. So we take the derivative with respect to x of the sine of y, set that equal to the derivative with respect to x of x. Now the derivative of the sine of y with respect to x requires implicit differentiation. To start with, the derivative of the sine function is cosine. So we're going to get the cosine of y. Then because the inner function is y, we apply the implicit differentiation, the chain rule. We get y prime. So cosine y times y prime. The right-hand side, the derivative of x with respect to x, well, that's just 1. And now we can solve for y prime. Y prime is equal to 1 over the cosine of y. Okay? And we could leave it like this if we knew what y was, if we in fact knew the cosine of y. But we really want to do better than that because we want to know a formula that tells us the derivative of the arc sine of x. That's if we know the input x, we want a formula that will tell us the derivative when we're using that value of x rather than solving for y. So what is the cosine of y? What is the cosine of y? Well, we had the sine of y is equal to x, which again, by right triangle trigonometry, this is one way we could look at it. By the right triangle trigonometry, the sine of y equals x means that for this angle y, we have an opposite side of x and a hypotenuse of 1, and we can solve for the adjacent side, which gives us the square root of 1 minus x squared. And using this same triangle, the cosine of y, which is adjacent over hypotenuse, would equal root 1 minus x squared over 1, or just root 1 minus x squared. So we now have an expression in x for the cosine of y. So back to our y prime. Okay, y prime is equal to 1 over the cosine of y, but the cosine of y is the square root of 1 minus x squared. So y prime is equal to 1 over the square root of 1 minus x squared. Okay, so we have it. The derivative of the arc sine of x is equal to 1 over the square root of 1 minus x squared. As long as we are within the domain of the arc sine function. And the domain of the arc sine function is again where x is between -1 and +1. But for the derivative, we have to remove the -1 and the +1, or we would have undefined here. So there's the domain for the derivative. Okay. So the domain for the arc sine function was -1 to +1 inclusive, but the domain for its derivative, okay, is -1 to +1, the open interval instead. Okay, let's try this process again. Okay, to find a formula, okay, for instead the derivative of the arctangent function. The arctangent function. Okay, the derivation of the arctangent function. Let's start with the tangent. Okay. So tangent, looks like this. All right, here's our graph of y equals the tangent of x. Okay, and it repeats. Okay, it passes the vertical line test. It fails the horizontal line test. So we have to find a restriction. The restriction that we choose for the tangent function to build its inverse is to choose this window here. And that window is between -π/2 and +π/2, right, where these two vertical asymptotes are located. The next one over would be at 3π/2. Now, because these are infinite discontinuities, -π/2 and π/2 are not going to be included in the restriction. Alright, so let's graph the restriction. Right, -π/2 to +π/2. So this is y equals the tangent of x with a restricted domain of the open interval from -π/2 to π/2. Okay? That is our restricted domain. Restricted, so now the horizontal line test is passed. So now we can invert it. So now we can build the inverse. We can switch the x's and the y values. Okay, so we get two horizontal asymptotes. All right, so this is y equals π/2 and y equals -π/2. Okay, and the graph be something like this. All right. There's our arctangent function then. Y equals the arctangent of x. All right, so now let's find the derivative of the arctangent then. So we have the derivative with respect to x of the arctangent of x. So we let y equal the arctangent of x. Then by invertibility, that means the tangent of y is equal to x. And we can interpret that geometrically through the right triangle. There's one way we can interpret it geometrically. If this is the angle y, then the opposite side could be x and the adjacent side could be 1, and therefore the tangent of y is equal to x over 1. The tangent of y is equal to x. Now we can take the derivative of this equation using implicit differentiation. The derivative with respect to x of the tangent of y equals the derivative with respect to x of x. Now the derivative of tangent is secant squared, we recall. So derivative of tangent y is going to be secant squared of y times y prime, and that's the implicit differentiation. Okay. On the right-hand side, the derivative of x with respect to x is 1. Okay, so now we have y prime is equal to 1 over the secant squared of y. And one way that we can reinterpret this in terms of x, is to go back to the triangle. We can find the secant of y using the triangle. Now, secant of y is the hypotenuse divided by the adjacent, the reciprocal of the cosine. And we already have the adjacent side here is 1. But the hypotenuse we need to solve for. What's the hypotenuse? By the Pythagorean theorem, we have that the hypotenuse is 1 squared plus x squared. All right, that equals the hypotenuse squared. All right, so the hypotenuse is the square root of 1 plus x squared. So square root of 1 plus x squared is the secant of y. That's the secant of y. Well, we want the secant of y squared. Okay, so we get 1 over the square root of 1 plus x squared squared. In other words, then the derivative with respect to x of the arctangent of x is equal to 1 over 1 plus x squared. And similarly, you can derive all these other formulas as well. Now, once we have all the formulas derived, we now know how to find the derivatives of the inverse trig functions. We can start using them to find further dy dx's. Let's try a couple more examples here. Example. Find y prime if y equals the arcsine of the square root of the sine of x. Okay, so dy dx, that's the derivative of the left-hand side, equals the derivative of the right-hand side. Okay, on the right-hand side, we need to apply a chain rule first on the arcsine. Now, the arcsine, we just found, all right, the derivative of the arcsine of x is 1 over the square root of 1 minus x squared. So the derivative of the arcsine of root sine x is going to be 1 over the square root of 1 minus the square root of sine x squared. Okay, we leave the square root of the sine of x alone while we're applying the chain rule. Then we multiply that, okay, by the derivative of the square root of the sine of x. Okay, so we have 1 over the square root of 1 minus the sine of x. The derivative of the square root of sine of x is going to be 1 over 2 root sine x times the derivative of the sine of x, another chain rule. And the derivative of the sine of x is cosine x. So we now have 1 over 2 root 1 minus sine x times root sine x times cosine x. So altogether, cosine x over 2 times the square root of the sine x times 1 minus the sine of x. Okay, and that would be the derivative of the arc sine of the square root of the sine of x. Okay, so this is not one where we use the implicit differentiation within the formula itself, actually. We used implicit differentiation to figure out this derivative of the arc sine. Okay, is this 1 over root 1 minus x squared. But instead we actually used the chain rule here. Okay, this was a chain rule. And this was a chain rule as well. All right, so we had to apply the chain rule twice. Because we had a composition really have three functions. The inner function was the sine of x. It was inside of the square root function. And that was inside of the arc sine function. So we had to apply the chain rule twice. Okay. Find y prime if the arctangent of xy is equal to 1 plus x squared y. Okay, now we need to take the derivative with respect to x of both sides. The arctangent of xy on the left and the derivative on the right of 1 plus x squared y. So on the left, first we need the derivative of the arctangent, recalling that the derivative of the arctangent of x is 1 over 1 plus x squared. So the derivative of the arctangent of xy is going to start with 1 over 1 plus xy squared. And then by the chain rule, we would multiply that by the derivative of xy. On the right-hand side, we can distribute the differential operator. The derivative of 1 with respect to x is just 0. And then we need the derivative with respect to x of x squared y. So take the derivative of xy, and to take the derivative of x squared y, we would need the product rule. Okay, so this is a product rule, and this is a product rule. So we have 1 over 1 plus xy quantity squared. Product rule on xy, let's see, take the derivative of x, that's just 1, and leave the y alone, so 1 times y, plus x, leave that alone, times the derivative of y with respect to x, which is y prime. Other side, we have first a derivative of x squared, which is 2x, and then leave the y alone, plus, now we'll leave x squared alone, and the derivative of y with respect to x, which is again y prime. Okay, and now we were asked to find y prime, so let's solve for y prime. Okay, so I'm going to multiply first both sides by the common denominator, the 1 plus xy quantity squared. So I have y plus xy prime is equal to 2xy plus x squared y prime times 1 plus the quantity xy squared. I'll do some expansion. Y plus xy prime. Okay, on the right we have what? 2xy times 1 plus xy. This right here, this square should actually be right here, right? Xy squared, like that. So we have 2xy times 1 plus xy squared. Okay, and then plus, and then we have x squared y prime times 1 plus xy squared, like so. So I want to isolate the y prime terms. Okay, so we have y plus xy prime on the left. On the right, let's see, we have 2xy plus 2 times, this would be x to the third, y to the third. Okay, plus, okay, now I have y prime times, I'm going to distribute this x squared to get an x squared plus x to the fourth y squared. Okay, now I'll move the y prime terms to the left, so I have xy prime, leave that there, minus y prime times x squared plus x to the fourth y squared. Okay, so I've left this on this side. I brought this over to the left-hand side. And I'm going to bring this y over to the right-hand side instead. Okay, so that shows up as a negative y. Okay, and then we have a plus 2xy plus 2x cubed y cubed as well. Can factor out y prime on the left, y prime times x minus x squared minus x to the fourth y squared. Okay, equals this group of terms here, right? Negative y plus 2xy plus 2x cubed y cubed. And now we can divide both sides by this quantity right here. So y prime is equal to negative y plus 2xy plus 2x cubed y cubed divided by this quantity x minus x squared minus x to the fourth y squared. There's our very nasty looking derivative that we get for this function. The arctangent of xy equals 1 plus x squared y. Okay. So the calculus can get quite complicated, but it certainly does clean up a lot of the algebra that we would otherwise have to do from the other processes we've talked about previously. But there's still a lot of algebra that is involved in doing these exercises as well, certainly. Okay, now take a look at the worksheet exercises. I give you some answers here. Let me know if you run into any typos. I don't believe there are any, but in case you run into any, or if you want to talk about any of these, just let me know. Okay, find dy dx. Some of them are a little nastier than others. Let me know if you need any help. Okay, find equation of tangent lines. You'll see similar exercises in your homework as well, deriving these formulas, and a couple of the inverse trig equations as well. And that's it for this section. You can let me know if you have any questions. Take care.